Okay, so which one are we looking at here? Tell me. Probably skip this one. Skip this guy, I'm assuming. Tell me, will you tell me when we want to do one? Going once. Those are so hard to see. This is use first derivative test to determine local extrema. Just polynomial. These aren't too bad. Yeah, I think we can just skip these. Okay, this has got a square root in it. Okay, let's look at this one. Can I make that bigger? All right. Okay, there we go. Find the intervals on which this function is increasing and decreasing. Identify the function's local extreme value, so relative extrema, if any. Okay, and then we'll just, I don't know what, that's really, if any, saying where they are taken. Oh boy, that's bad, isn't it? We'll look at the choices and see what that means. Which, if any, of the extreme values are absolute? Okay, so what do we do? Okay, and this function up here, when it's written with a radical like that, what do we probably want to do if we're going to be doing some differentiation here? Good, write it as fractional power. So we've got g of x equals x times the quantity 18 minus x squared to the 1/2. Okay, and there's no interval imposed here. What? So differentiate. Okay. How are we going to differentiate that? Now, if you kind of blur your vision here and you look on a big scale, what's the first derivative rule that applies here? Okay, good. Product, not power, right? Because we've actually got a product of two factors. One of those factors is going to involve a power, right? But it's at the outermost level, I've got a product of two things. So I got to use the product rule. Okay, so talk me through that. What do we got? X times, oh yeah, the derivative of that whole thing. So that's going to be a chain rule issue, right? Now, when I'm differentiating the second factor, what's the first layer of that derivative? Power. Right, I got something to the 1/2. What's the derivative of something to the 1/2? Okay. 1/2 something to the negative 1/2, and the something is an 18 minus x squared. So if we look at that second layer then, inside the power we've got this polynomial 18 minus x squared. We've got to differentiate that. That's the next link in the chain, right? So what is the derivative of 18 minus x squared? Negative 2x, okay? So we had a two-layer chain rule. Now we'll have to do the other part of the product rule. Second factor times the derivative of the first, and this one. Okay, so there's our derivative. That looks pretty ugly, but we clean that up a whole bunch. What, you see any common factors? We're looking for like bases here. Okay, there's an actually there isn't an x. We don't have any x's over here in this. And keep in mind that here is the plus sign that's linking this whole thing right here is term, call it term number 1, and this little guy over here is term number 2. So we're looking at common factors of the two terms. When we look for common factors, we're looking for like bases, bases that are maybe taken to different powers, but like bases. What do you see? Yeah, we see 18 minus x squared to different powers here, right? So we can factor that out. There's more than one ways to do this, by the way. And algebraically, you can take many different routes. And some people prefer to just maybe write this as a fraction and then get common denominators and things. I really believe in the long run it's much easier to just factor out like bases. And we'll see more of that even this year. I think that'll become real clear. So we got like bases. Here's our like bases. These guys. When I'm factoring out common factors like bases, I can only factor out the smallest of the powers, right? So which power of this base, 18 minus x squared, am I pulling out of both terms then? Negative 1/2. Negative 1/2 is less than positive 1/2, so I'm going to divide that out front. All right, so we're going to be left with, hard to see. So we've got our 18 minus x squared negative 1/2, and then I'm just going to open up a set of brackets for all the other stuff that's left over. And here's going to be my plus sign. So I'm going to have the first term leftovers and the second term leftovers in there, right? Now, from the first term, let's go ahead and clean some things up while we're at it here. If I look at the other parts of that first term, x times 1/2 times negative 2x, what's all that going to simplify to? Negative x squared, the 2 and the 1/2 cancel, but I still have that negative, so negative x squared. I guess I didn't need quite all this room, did I? Okay, and then this goes away completely, right? Give myself a little more room over here. How about over here? If I'm factoring out my base, 18 minus x squared, to the negative 1/2, I just completely divided it away from the first one, right? What am I left with over here, though, if I divide away this base to the negative 1/2 power? Keeping in mind that factoring is a process of division. When I factor things out, I'm dividing them away from each term. Good. Okay, so I'm taking the base to the 1/2. Just to simplify things for a second here, let's call the base, just call it b. I've got b to the 1/2 divided by my base, just call it b, to the negative 1/2. That's what I divided out front. And we know our exponent rules for that. If I'm dividing like bases, I'm just going to subtract exponents, right? So that's b to the 1/2 minus negative 1/2, b to the 1, right? And it's been a while since we've done a lot of this, but we saw that pattern, that's what happens. Not surprising, if you think about this, and I'm looking at this real conceptually and kind of theoretically here, if I divide the base away completely from the first term, then really that's just the base to the 0 power is what's left, right? By the derivative process, didn't we just ratchet down the power of that by 1 when we took the derivative? Right? Remember, we took the exponent down front and subtracted 1 from the exponent. So it's not really a big surprise if we kind of think about this a little bit, that if the first term has the base to the 0 power, the second term would have to have the base to the first power. They got to differ by 1, the exponents, right? So we're left with then 18 minus x squared to the 1. Okay, make sense? Okay. Okay, and now we got we've differentiated. That's looking pretty good. Maybe let's go ahead and simplify this one more step. What can we do with this first factor? Yeah, good. We've got this negative exponent, which means we're going to push it to the bottom. Negative exponents go on the bottom. And then we can combine like terms over here. And so we're left with g prime of x equals, we're going to have a big fraction. On the top, what do we get? Okay, plus 18. Okay, so 18 minus 2x squared on the bottom. We've got 18 minus x squared to the 1/2, so I could even write that as a square root if I want to now, right? And there's my derivative. That's nice. We got it set up as a rational function, and so we know we got stuff on the top and stuff on the bottom. That's convenient because when we're looking for critical numbers, where are the critical numbers going to be? Where are we going to look for them, I guess?
Zero.
Undefined and 0, right? And a fraction is equal to 0 when the top equals 0, right? So we'll look for, we know that g prime of x will equal 0 when the numerator is 0. That makes things simple for us. Okay, and that's an easy one to solve. What could I do to solve that? Algebraically, what's our strategy? Could probably factor it, but we can make it easier. Say it again. Yeah, how'd you get it? Okay, good. In other words, okay, the point and that's good. I think I'm sure everybody sees this, but I'm just going to reinforce it anyway. Because I've only got an x in one spot here, I don't need to go through the process of factoring it or anything. I can always, if I can point to a single x, I can isolate it algebraically. So we'll add 2x squared to the other side, divide by 2, right? That gives me something like x squared equals 9, so therefore x equals plus or minus 3, right, by square root. Okay, so there's two critical numbers. Now, we got to find the other species of critical number where it's undefined. You already told me, where is g prime of x going to equal 0 if it's written as a rational function, fractional function? Function is undefined, fraction is undefined where? Bottom 0. Okay, so we got to look on the bottom here. Okay, now where? It's undefined when bottom equals 0. Now there's another thing we got to be careful of here too, though, isn't there? Where is our function? And if we look at our original function here, well, we'll go back up and deal with that in a second. So g prime of x is undefined when 18 minus x squared equals 0, right?
Or negative.
Or negative. Okay, good. I'm glad you bring that up because we're saying negative because we've got a square root on the bottom, and we actually have two rules to be careful of, right? We can't divide by 0, and we can't take an even root, meaning square root, fourth root of a negative number. Okay, but we're going to get a lot better at this too in the next week and a half or so as we start to move into focusing more on this functional analysis using calculus. The first step that we're going to end up always doing is before we even do the calculus, we're going to look at the original function, and we're always going to try to analyze the domain. We'll get some practice with that here soon, some more practice with that. Because we know that where the domain exists, we're going to look for critical numbers. But any place where a function is undefined, where the function doesn't exist, do we need to look for critical numbers? I mean, critical numbers are important because the reason we're looking for those, remember, is we're trying to find peaks and valleys, right? Relative extrema, and maybe inflection points. But could there be a peak or a valley in a place where the function doesn't even exist? No. And so we only look for critical numbers, and this is something to be careful of because it really pares down the process and makes it easier and more efficient. We're only going to look in places where the function is actually defined, right? So if we were to go back up to our original problem here, where we've got this square root of 18 minus x squared, where is our, I don't need specifics, but based on that function, where is our function not even going to exist? If I've got a square root in this thing. You finish the sentence. The function will be undefined for the values of x where the square root is negative, right? So we could look at this stuff in here, inside the square root, inside the red bubble. Any place where that red bubble is less than 0, the function's going to be undefined anyway, isn't it? Right? So any place where 18 minus x squared is less than 0. Now that's going to be the same place as down here where the square root on the bottom is negative also. Okay, and so for that reason, we don't really need to look for critical numbers where the square root on the bottom has a negative argument. Does that make sense? Okay, because that function doesn't even exist there. So what if we, real quick, now this is getting real crowded, I'm just going to go to the next page real quick. And what if we just take this, let's go ahead and find the domain. So if I solve this, I want to find the places where the function is undefined. Actually, it might even be easier while we're at it. Why don't we just find the places where it is defined, right? So we could just kind of erase this one if we can. No, of course we can't. So let's just ask, where is the bottom, or excuse me, where is the argument of that square root? Where is it okay? Where is it non-negative, greater than or equal to 0? So how would I solve this inequality? Well, I could move the 18 over, or I could even move the x squared over if I wanted. 18 is greater than or equal to x squared. Maybe I'll turn that around. Say x squared is less than or equal to 18. So now if I just square root both sides, I got it, right? So this is a little bit tricky. If I square root both sides, I kind of unexpectedly got into some other review here, but this is more algebra review. This is good. If I square root both sides, what is the square root of x squared? This is a little tricky now. Think about this. Well, we're used to doing, oh, this is good. This is good stuff. It's good stuff to be reminded of. We're used to seeing this in the context of something like this. What if I'm solving the equation x squared equals 4? You guys know, and pay close attention to this, because this is something that a lot of people sort of forget about, that it's important to understand why this works. You all know that the next step is to say x equals what? Plus or minus 2, right? That's a very natural step. You guys are really good about that. Why is that, though? Okay. The reason that that's the case is when I square root both sides, a lot of textbooks really state this incorrectly. It's the square root of 4 is not plus or minus 2. The square root of 4 is 2. That's it. The reason we get the plus or minus is because the square root of x squared is technically equal to the absolute value of x. That's the definition of absolute value. If I take the square root of something squared, when I square it, doesn't that ensure that it's always positive, right? Even if x had a negative value, when I square it, it makes the square positive, and then square rooting it gives me back a positive answer only, right? And so really this is technically equal to the square root of x. Well, if the square root of x equals 2, that's where the plus or minus comes in, right? Because we know that if the square root of x is 2, then x equals plus or minus 2, right? It could be either one, because the answer is going to be made positive by the square root. So that's where that plus or minus comes in. So if we go back up here, when I square root both sides, what I've really got is the absolute value of x is less than or equal to the square root of 18, so what, 3 radical 2? Yeah. Does that make sense? Now what's that going to look like? If and this goes clear back to algebra 2. If the absolute value, tell me what you did in algebra 2 in this situation. If I have an absolute value function, I think it looked like this. We did something like the absolute value, we were doing linear stuff at the time probably. See, what'd you do? Absolute value of ax plus b is less than c. What did you do about that? That's equivalent to saying what? Do you remember? Okay, yeah, there's going to be a negative c. The question is, we're going to come up with a compound inequality. Is it this one? Is it ax plus b is greater than c, or ax plus b is less than c, or is it the alternative, is the other compound inequality, ax plus b is greater than negative 2, well, sorry, negative That should be a negative c. Negative c. Gosh, where did I get the 2? And less than positive c. Is it an or an and inequality if the absolute value is less than c? Do you remember? It's an and. It has to be an and. And the reason it has to be an and, there's a way you can also kind of internalize this, because an absolute value is always just a distance, right? We think of it as distance from the origin or a distance from a center or something like that. If the distance from the center of this interval is going to always be less than some maximum value, then that means we could go either in the positive or the negative direction a certain amount, but we're trapped between those extremes, right? So a less than always means an and. And we could rewrite this as x is greater than or equal to negative 3 radical 2 and less than or equal to positive 3 radical 2, right? So that's our domain. You know, we haven't talked a lot about this. That's really, that kind of comes up, like I say, in the next week and a half or 2 weeks, we'll look more at this, but might as well get that on the radar now a little bit. So that's the only place our function lives, and therefore that's the only, there's the domain within which we want to look for critical numbers. The problem didn't say it explicitly, but it could have. It could have just said, while we were at it, on the interval, negative 3 radical 2 to positive 3 radical 2, because that's our domain. Okay? So if we go down here, then we could solve this. Well, where is that going to be true? Where is x squared, 18 minus x squared, going to equal 0? If I do the math, isn't that just the endpoints of our domain anyway? If I solve that, right, I just get x squared equals 18, so x equals plus or minus the square root of 18, 3 radical 2. So here's another kind of a subtle question. Are those considered critical numbers then, if this is our domain? Are those considered critical numbers? See the question? If our domain is all values of x greater than or equal to negative 3 radical 2 and less than or equal to positive 3 radical 2. So these are the endpoints of our interval. Are the endpoints, could they be considered critical numbers? I don't think there's even, probably you could argue, you know, strongly either way. I think most people would say no. The endpoints don't really count as critical numbers because you're going to check those anyway. Critical numbers have to be the internal numbers between the endpoints where we get 0 or undefined first derivatives. Okay? Not a big deal. I'm just throwing it out there for you. Okay, so then we've got the only critical numbers that we have inside the edges of our domain where our function lives are these two. Whoops, those two, right? Plus or minus 3. So we could just go ahead and make our little table and analyze this thing, right? Okay, so this is a bigger problem than I thought it would be. So let me grab a couple things and go to the next page. How about if we do so there's our function. Let's grab our derivative. There's our derivative. Okay, everybody with me? And then critical numbers, we said we're just at plus and minus 3. Our domain. let's make our table. Are you getting more comfortable with the table? You're going to learn to love the table, I promise you. So there's our domain represented on the table. We had two internal critical numbers. Let's see, we had -3, +3. How do we know those are critical numbers? How can I show it on the table? Okay, good. Zeros of the first derivative. Good, so we know that these are horizontal tangent lines. Okay? And it wants us to use the first derivative test. And by the way, even if it didn't say that, there's no reason that we would ever want to do the second derivative test, because to do so, we'd have to differentiate this quotient, right? And so unless we explicitly had to go get the points of inflection and really needed the second derivative, we would avoid it like the plague. We would not want to deal with that derivative. We would just default to the first derivative test. So let's, first derivative test, what do? Choose test points. So probably 0 would be a good in-between test point, right? And let's see, over here between -3 and -3 radical, what is -3 radical 2? So that's -3 times 1.4, what is that? That's going to be bigger than 4, isn't it? Right? So we could just say something like -4 and +4, okay? And let's check the signs of the derivative there, and we'll see what happens. So at 0, what's going to happen? It's going to be positive or negative. So all we care about is the sign. If I put 0 in for x there, positive. 18 over the square root of 18, right? Because the x terms would just go away. So I get positive. What about at 4? Now we're just going to try to find the sign of the numerator and the sign of the denominator, and then we'll just determine the overall sign from that. So what about the top? 18 minus 2 times 4 squared is that, what's the sign of that? 18 minus 2 times 4 squared. Negative. We don't care exactly what it is, but clearly it's negative, right? So I'm going to get negative over, what about the bottom? 18 minus 4 squared, positive. So negative over positive is an overall sign of negative, okay? And I'm going to get the same thing for -4, aren't I? Because all the x's are squared, so it doesn't even matter if I'm putting in positive or -4. I'm going to get the same result either way. It's an even function. So what do we got then? What is this critical number? I mean, what's the behavior of the function here? If we're going from negative first derivative to positive, so what's that going to be? I'm going left to right. Give me valid, because I'm going from decreasing function to increasing function, so it's got to be like that, right? Make sense? Over here, I'm going from increasing to decreasing, so it's got to be like that. Agreed? Okay. And then the question, so we found the x value where we get a relative minimum. We found the x value where we get a relative maximum. If they wanted the points, and I won't even, this is getting really long, but if they wanted to know the actual points and not just the x values for our minimum and maximum, what would I do? Good, I'm just going to find the value of g, right? So I'm going to fill in, here's my ordered pair. Here's my ordered pair. I'm just going to plug -3 into my original function to find out what the corresponding y value is, and then I'd have a point. I could plug +3 into my original g function to find out what the y value is there, and I'd get the points. Okay. They want to know, they also wanted to know, I think they want to know what the absolute extremum was, what the absolute extrema were on that interval. So how would I know that then? I would have determined the y values of the two critical numbers, but I've got to compare those to the y values where? At the endpoints, right? So I'd also have to find out what's the y value there and what's the y value there, right? So I'd evaluate the function at those 4 places. The largest y value would be the absolute maximum, and the smallest y value would be the absolute minimum. Okay? I mean, we could probably not do that part, right? Okay. You guys can do that. What's that?
We just put it in our calculator.
Well,
And just star X.
yeah, right, yeah. Okay. And you could use decimals too. It'd be fine, because you're really just trying to, you just want to know which one is the absolute maximum. You can just compare decimals. It's fine. They get a good way to compare magnitudes. All right, so see how we doing for time here? Wow, calculus. I loved it. When I taught in McMinnville, we had 70 minutes every day. It was just awesome. I mean, it was really nice in calculus. Okay. Do we want to take a quick look at that? Oh yeah, this is good. There are a lot. This is a good one. I made the same mistake you guys were making when you first looked at this one. Okay, the instructions say, and you probably can't read this. Use the graph of the function f prime, not f. And I made the problem of just looking at this and assuming that it was the actual f that was graphed. It's not. It's the derivative of f that is graphed, which makes it easier actually to estimate the intervals on which the function is increasing or decreasing. Also estimate the x-coordinates of all the local extreme values. So here, I'll make this even bigger. So here's our function. This is f prime of x, right? So I want you to tell me then, don't say it out loud yet, everybody look at that. See if you can identify the intervals where that function is increasing based on the graph of the first derivative. It's hard to see the numbers, but here, let me draw in some, let me draw the numbers in there. So this is that's -3. This is, let's see, that's 1, so that's -2 right there. This is -1. And this is, yeah, and this is -4 right there. Okay, so where is the function increasing? Okay, and I don't even really care about specifics, but how am I going to know on the graph? Where is the function going to be increasing? Okay, where the first derivative is positive value, right? Positive first derivative means increasing function. And so that's going to be on this portion of the graph. Open circle there, open circle there. It's going to be that part of the graph. Or that part of the graph. Right? Okay, so we would just say then on the interval, these should be rounded brackets, because when the derivative is actually 0, it's neither increasing nor decreasing. Right? That's going to be a level spot, a horizontal tangent line. So it would be values of x greater than -4 and less than -2, or -1 to infinity, so greater than -1, right? So then it would be pretty easy to find the decreasing ones, isn't it? So it's going to be decreasing on this part and that part, right? So values less than -4 or between -2 and -1. Okay, now which one is a maximum of those critical numbers where we're transitioning from negative to positive or vice versa? Based on this graph, let's point to all the maxima and all the minima. So the maxima of the function, not the derivative, but the maxima of the function. What about this guy right here? Is this going to be a maximum or a minimum? Ah, how come? Makes sense? It's going from decreasing to increasing. What does that look like? That's going downhill to going uphill. So that's going to be a minimum. What about this one right here? That's a maximum, isn't it? Because I'm going from positive to negative first derivative. So from increasing to decreasing. And what about this one over here then? That's a minimum, isn't it? Okay? Make sense? Well, that's a good question. I like that question. All right, we have to, maybe one more. Oh. Did I skip one? Yeah, we did that guy, okay, never mind. The rest are from the book, okay. And then the book ones, we're obviously not gonna get through a complete one today, but we'll get in here again soon. We wanna look at a trig one. We can't even see the functions here. Okay, yeah, we'll look at it, but we're not gonna have time to do this. By the time I pull it up, we won't have time. Like I said, 3-4 assignments up. You know, first priority, I would say if I were you, first priority when we're in the lab, next couple of days, finish up, retake any tests you wanna do. You know, the end of the semester is coming soon. But then as you kind of get to that point, work hard on getting through 3-3 and 3-4. I really want, like next week when we're kind of done with this first semester, I wanna jump back into this big time. Okay, we'll do our next, we don't have a test coming for a little bit. We'll do a test when we get up to section 3-6. Okay, 3-6 is a summary of the first 5 sections. That's a good place to do it. All right.